Bonjour à toutes et à tous. Bonjour, Lorenzo Cominelli. We are sorry for that a little late, but we are very glad that you are here with us. Today we have the great pleasure to make that hybrid conference. We are here at Paris 8 with Lorenzo Cominelli, and we open also that webinar by Zoom for all the people that are with us. Lorenzo, we are very happy that you are here. Lorenzo Cominelli, he's a postdoctoral researcher at the Information Engineer Department working at Piaggio Research Center of the University of Pisa in Italy, and he worked with the Professor Enzo Pasquale Siciliano and all their team to the new prototype, Abel, and this is also the meaning of the title of that session, Meeting Abel and Humanoid Prototype to Investigate Emotion, a prototype very particular and that you will talk today, because you have imagined that prototype to feeling the emotion and capturing the emotion of the audience, of the people, and work with that. So you will present that prototype, but also the humanoid robot face, facial automaton for confining emotion, sorry for my English, and of course the aim for us is to understand how could the actor interact with that kind of prototype of robot, humanoid robot, and what it means to have that such kind of prototype on stage. So thank you to be here. We are very glad. I give you the microphone for that session that will be on only one part, and at the end we can take some questions about the audience here and by Zoom. Thank you so much.
Thank you, Julia, for the presentation. So I will be very quick with this slide because she already said everything. Anyway, I'm a biomedical engineer, basically. So anyway, I will try to be not too technical in this presentation. I will talk a lot about face, which is the robot that you see in the upper part of this slide. And we can consider the mother of Abel, which is the novel robot that you can see downside. So I want to show you, I have a lot of material. I hope to be able to show you everything. And we will see a lot of things about face because it's the robot that we used until the last year. But don't worry, because everything that I show you about face apply also for Abel, because all the software and the systems that we develop are portable and can be used also for this new robot. So let's start from fundamental premise. I will talk a lot about emotions. Why? Because emotions are very important in certain fields of robotics. Do we always need emotions? Not. Because, of course, this is an example of industrial robots, so robotic arms, soldering components in a factory. Here we are not interested to include emotions in these robots. At least we are interested, for example, in that this robot can understand emotions or conditions of stress if they are cobots, so they collaborate with workers. But we don't have to make this robot sad or happy while working. Another more evident example is this one. This is, I don't know if you know this robot, it's the Leonardo da Vinci robot, so it's a surgical robot. And of course, do you care if this robot is sad or had a bad day? Well, of course not. You want this robot to save your life. So emotions are not something that must be everywhere and in every robot, okay? So this is a premise that is fundamental. But they are mandatory in a particular case, social robots. Why? I took this definition, it's not the most recent, but I like it, by Bartlett and Forlizzi. Oh, when you see this kind of things, like this square with this kind of writings. These are citations. So if you are interested, you can deepen an argument just taking notes of the paper. So what is a social robot? Here is written that it's autonomous or semi-autonomous, but it's better if it's autonomous. Robot that interacts and communicates with humans. And I love this part, by following the behavioral norms expected. And by who? By the people with whom the robot is intended to interact. So this is fundamental, and this is why I will talk about emotions, because emotions are ubiquitous in our communication. So every time we communicate between humans, we make expressions, we make gestures, we make, especially if you're Italian like me, so it ends with a lot of body gestures and things like that. And this is something that distinguishes us from all the other creators that we know. I mean, this emotional intelligence that we have, these empathy capabilities. And this is why we are investigating these things in robots. These are things that are very important also for the application of these robots that are typically used in medical context for children with autism spectrum disorder or dementia, Alzheimer's. So you need to understand if there is an emotional reaction in the subject who is interacting with the robots. Okay? And emotions are important in every aspect of this robot, in the design, in the materials in a sense. They have to be able to understand emotions, to convey emotions. And also something in their cognitive system, in the processing of emotions must be similar to us. Okay? But how can I recognize a social robot? This definition is very general, no? So it's easy to understand that this one, which is Sophia, the Sophia robot, made by David Danson. Also Face has been made by David Danson. Face can be considered as the older sister of Sophia, no? It's easy to understand that she's a social robot. Of course, the robotic arm is not a social robot, but it has been called that also this is a social robot. This is Jibo by Cynthia Brezel. This is more a commercial product, so you can see a reduction of everything, no? But it can interact, it can move this little body, it can perform some, they are not expressions, but it's expressive in a sense, no? With this little screen, okay? So this is the first lesson learned, that there are many forms of social interactive robots. They can be abstract, like this one, which is Emu. They can be biomorphic, so resemble the shape of an animal, like this one, which is used in Alzheimer's disease. And, or it can be more similar to a human, so more human-like, this is the term. No? So this trend that you see here with this green arrow is the human likeness, no? It is increasing, yeah, from the left to the right. But there is a fact that the comfort, the familiarity that you have with this kind of robot does not have this trend. And this comes from a theory. This is a big challenge for social roboticists, which is the uncanny valley. It's a bit old, it's from the 70s, from Masahiro Mori, this theory. And what it says, that the more a robot resembles a human, and the more that its familiarity increases. But at a certain point, you have a steep drop-off in this curve, which is the valley, so the uncanny means like discomfort, no? That you feel when it's too similar to a human, but not still a human. So you can see also that the effort is increased if the thing is moving or is still, okay? So what are the reasons of this reaction, this emotional reaction? There are several studies. One is a bit evolutionary, which is this pathogen avoidance theory. I don't like it so much, but anyway, it's easy. You see something that is strange, and the first reaction is to repulse it, because, I don't know, it can be some disease that you can be infected or something like that. And another one, which is more reasonable, is the conflicting perceptual cues, meaning that, everything can be summarized in these two things that I wrote at the bottom. So a categorization difficulty, so I don't know what it is. I don't know if it's human, if it's alive or not, and how should I behave with this agent, okay? And also a perceptual mismatch. So it looks like something that I know, but it's strange. it doesn't behave, it doesn't move exactly as I expected. Expectations. So it's a matter of expectations. We have a gap between what I see and what I expect to see and doesn't happen. So we can say that we are here with this kind of robots, no? Robots with the humanoid skin. So I can say that I'm working with the worst robots ever, but it's not like that. Meaning that this hypothesis is impractical. There are many critics to the uncanny valley hypothesis. The first one is that anthropomorphism and nor the emotional response can easily describe with a single variable, no? And it depends also on the cultural context. In fact, now you can see that there are cross-cultural studies in many countries. It depends on habituation, so you can have short versus long-term interactions. You can have a first reaction, but then you can, I don't know, get habituated to a certain form of agent. There are different exposure to robots. Let's think about Japan, no? It's different from here, so they are more habituated to see robots. And I mean, it's a matter of expectation. And we have two ways to get out from this valley, no? You can climb the mountain on this side, and this is the choice of Cibo, for example, no? You can lower the expectations. So the gap is reduced because the agent, the artificial agent, you cannot expect so much cognitive abilities, okay? And so the gap is reduced. Or, and this is the harder climbing, you can go for the pink road, so towards the human. How you do this? You do this evolving the robot movements realism, first of all, improving, and this is very important, the cognitive capabilities of the robot. So you have to reduce this cognitive mismatch and make correspond what you expect from this agent to what you really then see then, okay? And there is a reason to take this direction, which is motor resonance. So what it is, this has to do with mirror neurons, for example, with empathy, with a lot of things that, I mean, the fact is this, if I see something that is very similar to me, it's easier for me to feel something, okay? It's easier that this thing makes me feel something because it's very similar to me, okay? So I have a resonance with this kind of objects. There are a lot of experiments, for example, looking at movements of a robotic car that can move in very different way, in a very robotic way or in a very smooth way. And I can see that I have activation in my neurons that are more active if the movement is more human-like, for example. The same is for expressions, the same is for many things. And this is very important because from motor resonance you go to social resonance. Okay, so if I want to feel bad because I see a person that is feeling bad, if this person is a very simple object, this doesn't work. Okay, so to have a very working transmission of emotion, well, I need this kind of agents, this kind of realism, this kind of believability of the object that I'm interacting with, okay? So let's go to something about the control of these robots, no? Because they are still robots, they appear like a human, but they are robots. So how can I organize this, the architecture of control of these robots? There are three main blocks, conceptual blocks for a control architecture of a robot, which is the yellow one, which is the sense block, so everything that regards perception. The other one is the green one, which is the plan block, so planification, pondering which action I have to perform according to what I'm seeing and what I'm perceiving, and then the actuation block, which is the red one. So there are two paradigms. This is taken from Rodney Brooks, which is one of the most famous roboticists. And these two paradigms, one is the reactive one, and one is the hierarchical one. The reactive one tells this: you have sensors that perceive something, and actuations like muscles or motors that immediately and directly depend on what the sensors perceives. Okay, this is how, for example, insects work. Okay, you don't have the plant block. You don't have a brain. You just have a connection, a direct connection between sensing and acting. And the body itself, how it's made and how the nature shaped this body makes the intelligence of this creature. Okay? This is in philosophy what is called behaviorism, for example. And then there is cognitivism, so the importance of the brain. And this is like a rover works, for example. So you take a lot of information with the sense block, then you understand how to, I don't know, for example, an optimization of a path to follow. I calculate to avoid obstacles, I calculate the most direct path to reach a point, and then I act. So I move a wheel or a leg, okay? I do a step, and then I calculate again, okay? So this is why there is this loop. Which is the control architecture of a human, according to you? I tell you the answer. It's not the first and not the second, but it's something in the middle. It's a hybrid. The reactive and deliberative architecture. What does it mean? It means that I can, for example, walk, so I can see, I don't know, a ground and walk, and while walking, I think about, I don't know, my girlfriend, the fact that I have to do a presentation here, or something like that, okay? Or another example, I'm cooking. I have a receipt in my mind, so I'm following steps. This is procedural concept that I'm doing with my brain, but accidentally I go near with my hand with a very hot object, and immediately I remove this arm. And this impulse, also electrically, doesn't reach my brain, so it goes from to the spine at the height of the arm and back to the arm, so it doesn't involve the brain. So we have both of these mechanisms. And this is why we follow this kind of architecture for designing the face control architecture. We will see also details about these modules. I mean, these blocks are conceptuals. All that you see here inside these blocks are programs that are in many computers, like taking information, processing it, and then giving something back. This information is then sent to another module. So we have this middleware, which is called EUR. There are many middlewares, just for the communication, that is responsible to take and bring the information, okay? But we can divide it in these blocks. We have some features, they are not so interesting. Modularity is very important because, for example, a team can work on a program and a team can work on another program, and they must be completely independent. This means that also you can extract this module and use it for a standalone project. I don't know, for example, you can use just the scene analyzer, which is a perception module for, I don't know, a security system, let's say. And it's very important to do this abstraction. So, for example, the brain is something that can work with a different actuation. What does it mean? What I've said before, that the brain that I've made for face, it can be the brain of Abel tomorrow, okay? And this is very important. The other is not so important for you. So, anyway, we can just, for the moment, think about these blocks like this: sense, plan, and act. Let's go inside these blocks and let's talk about these things. So let's start from perception, from sense. I guess that you already know which are the senses, so I will not say which are. But how does it work for social robots? I mean, they have to sense emotions. So there are cases in which you can make a touch capability. So you can use, for example, these smart materials that are sensitive to bending or to touch or to deformation. Typically you have a variation in the resistance of these materials, and so you can let's say, have control. But these things are more useful for manipulation, so things that have to pick a place, something like that, not just for interaction. It's also interesting to do some sort of sense of the body. This can be made with conductive ink that can be placed on the skin, for example, of a robot. In this case, this has been made for wearable technology to understand the movements of sport person, for example. But we can also apply this to a robot so that a modification in the movement can be perceived. You can, for example, distinguish caress to a punch or something like that. Then what? You can do electronic tongues or electronic noses. This is a paper of my first professor during my doctorate. And which is the problem with this kind of sensors, that they are not general tongues or general noses. They usually are very specific, so they can attach to a particular molecule, and you can understand the concentration of this molecule. So it's very difficult at the state of the art to build a general nose or a tongue. In this case, we have like something for discrimination of wine tasting and for oil. So these are projects that understand. Of course, they don't say that, wow, this is a wonderful oil. No, they just say if there are some components that are good or not, okay? Anyway, actually, how do you recognize others' emotion? You don't need to smell someone or to lick someone or to touch someone to understand how is his psychological or emotional state. So the first one is very easy, also because we are talking about face, so it's facial expressions, no? This is something very immediate, and we have a huge part of the brain which is sensitive to very small modifications in a facial expression of another person, okay? And this is the first one. But you as actors should teach me that the body also speaks, no? So you can have postures and gestures that explain how, or I can fake also this emotion, but I can represent my emotions using my body, no? A posture is communicative. A gesture is a movement, so you can also play with the speed of the movement, and you can express these things by the body. Another thing that is very typical in psychology is the proxemics, so the distance. You know that there are different bubbles in which you are in that are intimate or social, private, or public. So it depends also where you stand up in front of a person. Everything is different in the communication with this. Pay attention. I'm telling all these things, not just talking about you, but talking also about the robot, because these are the requirements that we have to respect for the robots, because the robots need to understand these things and should also be able to perform these actions. Okay? What is another thing which is less immediate? Well, physiological parameters. We are a bit weak in recognizing these things, meaning that they should be very evident, like this sweating guy is very exaggerated, no? Anyway, you can see if someone is blushing, for example, or if there is a pupil dilation, which is not really the case of David Bowie's pupil dilation, it's heterochrony, but anyway, just to put a big pupil in a slide. Or sweating, so if you are anxious, you can see these things, okay? But there are devices that can detect these things better than you. This is something that I anticipate. Oh, have you seen something? All these are non-verbal aspects of communication. And this is the big channel in which we understand emotions. It's not for the verbal communication. You can say whatever you want, of course, it matters, but we rely on these things more, okay? There is also a non-verbal property of verbal communication, which is prosody. You know what it is, prosody? We can say like this: prosody is everything but the text, is everything but the content. So it's the speed, it's the volume, it's the poses, it's everything that shape your sentence, which is not the textual content. So we can say that robots should rely most on audiovisual detection, no? Audiovisual system. And this is why we rely on audiovisual system. And you can put an integrated camera in the eye of the robot, which is a solution. It's a bit difficult because every time the robot moves the eyes, you have a change in the reference system. While for most of the image analysis algorithm, you should have a very stable image. And so the same for the ears. So we also have an integrated camera in the body for Abel and integrated microphones in the ears. But usually you use this kind of objects. I highlighted, I don't know if you, yes, it's quite visible. You know what it is? Are there any gamers here? No? Yeah, okay, so this is the Kinect, no? You know? It has been a bit of a flop in terms of commercial because players do not like so much this thing. So the idea is to use the body as a joystick, no? And this camera, there are a lot of kinds of this camera. So this is the old Kinect for the Xbox. This is the new version. We use them, but we have colleagues that use the Asus one, the Creative one. And they work all the same. Let's see what is inside this kind of cameras. So these are called RGBD camera, where the D stands for depth, okay? For 3D scan, okay? You have an array of microphones that are placed like this to understand the direction of the sound. Then you have a normal camera, so RGB, red, blue, green camera, like a webcam. But you have also a depth camera that needs two components, an emitter and a receiver. And this works like that. It's like if this device launch a net of infrared light, and this light, this pattern of light, comes back with a deformation according to the objects that encountered in this path. Okay? And according to this, you can have two images. The first one is this one, which is a normal images, where the color of the pixel is the color that you also see. And this one, where every pixel is the distance. The color of the pixel is the distance of that point. Okay? This one is an edging of the image. It's not important. So, what you are able to do with this kind of cameras to extract what is called the skeleton of a subject. So you always do like this with this kind of algorithm. You do a reduction of the information. Okay, so you don't need to. You can't bring all the information with you. So you reduce the information and having this kind of stick figure with the joints and the links between the joints. Okay, and so you have this effect. So from a person, you have the skeleton of the person. And you have a three-dimensional information on each point. But also the RGB image is very important. You can perform many image analysis algorithms. Usually they are based on machine learning and neural networks. So you extract, these are simpler, so you don't need a neural network to do this. So these are just operations that you perform on the image. For example, you can go down with the number of the colors for having some contours of the image. You can do a ground truth, so remove the background and make some salient image comes in the front. And you can also do these saliency maps. So saliency maps is a map in which a pixel is from white to black depending on its importance. So it's like the vision of the bee. This importance is given by a difference in contrast, a difference in the color. It's the point that you're looking at when you are very tired and you fixate a point like this. It's not a random point. It's a spot in the wall, it's an angle of a table, something like that. So this is just non-ponderate vision, let's say. Okay? This is very important because you need another point to look at. The robot has to look at the most important things, for example, the most important subject, but if there is no subject doing nothing interesting, the robot has to see something else, okay? So just looking at the environment, for example, okay? And still without the 3D information, you can do a facial detection and analysis of this face. So you can find in an image where is a face, you can crop the image, and then again, similar to the skeleton that you have seen in the Kinect, here you extract a mesh, so some important landmarks of the face, and you compare what the distribution of these points with, let's say, a dictionary that you know about a lot of expressions. And with these mechanisms, so with this training set that you have about faces, you can recognize emotions, you can recognize the age of someone, you can recognize the gender of someone, okay? And this is quite cool. I mean, it can be very useful. So, as I told you, we have a lot of modules inside the perception, the social perception of a robot. Have you seen how much emotions are crucial also in the perception? We are going to extract this kind of information. And this is the world seen by the robot. So you can see some students entering in the room. You can see the skeleton. This one is the direction of the sound, so this kind of arrow that you see upward. And, sorry, what else? You have the sound there. You have this pink one is the saliency point. I don't know why it goes there. It's nothing sexual, but it's just a contrast in the image. You have the facial expression. You cannot read here, but you have a percentage of probability that someone is doing a certain expression. So in each moment you have probability for every expression, every basic expression. So you can say that someone is, I don't know, 80% happy, but with 20% or 10% of probability is surprised. We visualize the highest probability, so the most reliable. You can see also that these squares are blue in case of a male, or pink in case of Chiara, so a female. And so, what the robot really sees is not this image. This is what the robot really sees. So it's an XML file. It's a structured file which is made by the middleware. And what you have here, you have all the informations given by each module. So let me highlight some parts. So this blue one, for example, is one subject. You can see subject there, slash subject here. Okay, so this is a subject. This, for example, is the position of the left hand in that moment. And you have these values, which are in meters, so according to the center of the field of view of the robot. What else? You have an happiness ratio, can you see? So 0.76. You can see this is exactly what I was saying before. The anger ratio is not 0, it's 0.21. But the happiness ratio is more probable. So probably she's smiling, or he is smiling, I don't know. What else? We have the saliency points, which speak another language. These are pixels. So, and these are another thing, but it's not so important. So this is what robots really see, a packet of information. And we have a trend which lasts 300 milliseconds. So we can say that with a frequency of 300 milliseconds, so 1/3 of a second, 3 times per second, all this information is given to the brain of the robot, okay? Oh, so let's say another thing. It has a shape of a human, but it's a computer, no? So we can connect this computer to other devices. So for example, we have used this kind of device, which is called lip motion, and it's like a Kinect for the hands. You can see that it is possible to see the movements of the hands. And for example, we can also detect eye movements using eye trackers. This is the most famous one, which is the Tobii. They can be glasses. So you can see, for example, also the pupil dilation and the movements. So where exactly a person is looking at. These are actually used for marketing, no? For example, you do the new website for Nike, and you want to know exactly where the subject is looking at. But I mean, this is something that also we can say, we can perform, we can do, no? To understand where someone is looking at or what he's doing with the hands. But we don't have to take these limits except for ethical reasons. What I mean that this robot and these computers and these machines can also go beyond our bandwidth, for example, in vision, in force, in everything, okay? So, for example, we can have super sense, extra-human senses, as in the case of affective computing. My professor, for example, is mainly focused on this part, which is affective computing. What is affective computing? All the devices that are able to extract information about your psycho-emotional state, reading your physiological parameters, cleaning this signal, analyzing this signal to understand what. Typical parameters are the heart rate variability, so you have a variation in your heartbeat or in your respiration rate. And another one that is very, very critical is the electrodermal activity. What is that? Is the truth, la macchina della verità, truth machine, no? You are connected to this kind of sensors that can be like contact sensors. And when you have an emotional reaction, your pores of the skin becomes more larger, and you sweat. So you release also a little quantity of water. Okay. What is a property of water? It's conductive. So if you put two electrodes, the middle, which is in the, how can I say this? That what is interposed between the electrodes becomes full of water, so it becomes more conductive. So you see a peak in the conduction, in the electrical conduction. And with this method, you can detect very small reactions that are not visible as the guy before that is super sweating. So Abel, for example, can feel if you are having an emotional reaction to something. Okay, this is something that we did also in an European project to understand, for example, if children that this is in the field of education, so with attention disorder, hyperactivity disorder. So we have these children, and we have the robots that it was a synthetic tutor, and the robots do this personalized learning, adapting the difficulty of the task according to the reaction of the children. And it's very important to use a multimodal approach. Why? Because this thing that I said before, so the fact that you have this reaction, is just quantitative, it's not qualitative. So if you have this reaction, that the child can be happy because solved the task, or desperate because can't solve the task, so, which is the opposite. But if you use a multimodal approach, so if you use the scene analyzer and the meta scene to see if a subject is smiling or is sad, you give a meaning to that physiological signal. Okay, so this is why you need many things. But let's go farther. So why use just the frequency of light that we can see? Why can't we use the infrared light? So there is a student in our lab that is working mainly on this, using thermal camera. If you look at some region of interest, like the nostrils, with this kind of cameras, you can understand the respiration rate without putting any device on the subject. No? So these are contactless. Or you can see the heart rate from the bloodstream, because the blood responds to the red frequency. Okay? And what is even most fascinating is that you cannot even understand emotions. Why? Because when you blush because you are angry, and when you blush because you are shy, is a different distribution of the blood on your face. You can have patterns, and these patterns correspond to different emotions. This is very interesting. So, one of the main objectives with Abel will be this of, let's say, create an extended multimodal perception. So, make him connect to to a lot of devices that can be wearable on the subject, that can be distributed in the room, that can be embodied in the robot. And according to all this information, the information, the estimation of the emotional state of the human interlocutor of the robot, well, this it becomes quite reliable, okay? This is the sense part. Let's go to the act part, so actuation, okay? Actuation, well, there are a lot of interesting actuators. This, for example, comes from soft robotics, so you can have this, typically you use shape memory alloy, electroactive polymer. So these are materials, smart materials, so are called, that react to, for example, a variation in voltage, perform some bending. So if you put modules and if you do some structures, you can have these fantastic structures that can walk and can perform some particular things. Then what? If you're looking at, if you feel amazed looking at some Boston Dynamics video, looking at Atlas doing parkour or Cheetah robot walking in the woods, I'm sure that you're looking at hydraulic and pneumatic actuators. So how do they work? They have this electro valve, and you have this quick release or removal of fluid or air, and so you have all these kind of movements, and you can also have these compliant movements to, for example, to going on different kind of grounds, okay? But if you're looking at, if you are talking about expressive robots like Face, like Abel, like Sophia, like Einstein, like this one, well, I'm sure that you will find inside the head of the robot servo motors. Why? Because they are small, because they are powerful, they can be very easily programmed, and they have a high repeatability in position, in motion, meaning that they quickly reach a position, and you can, with a high repeatability, perform this positioning whenever you want, okay? So how do they work? This is a bit technical, it's not so important. Look how simple it is to control them. You use the signal with this square wave, and just the duty cycle is called. So the percentage of 1 versus 0 areas gives the information about the position of the shaft. So you have this motor. These motors are used also for little cars, like or helicopters. Like, I don't know the English word for this, like modellismo, no? Like these things. Anyway, they are not even expensive, so you can have, there are kinds of servo motors, and you have a PID controller. It's not important that you know what it is, but it's just, let's say, an error-sensitive feedback control mechanism. So you set a position and you have an encoder, a sensor that tells you if you correctly reach the position or not and adjust the error. So yeah, this is very, very quick. And this is also what we place inside the head of Face and the head of Abel also. So what you see here, Face has this 3D printed skull, so this white thing, so this is like rigid plastic that you can 3D print. And the project of this skull is made to house the servo motors. And this is the very complicated part. This is the value of this thing, to design this kind of thing with a lot of motors inside and with a lot of wires or sticks that have to push and pull a facial mask without disturbing each other. No, this is the very value of this thing, because if you think about materials, this is plastic, silicone is nothing. It's this model servo motors. It doesn't cost a lot. What costs is thinking, conceiving this kind of object. Okay. And oh yes, the materials. So this one, can you see that there are some holes, some empty in this material, the frapper. I have put the copyright here because it's registered material from David Hansen, and this frapper I think is because facial rubber or something like that, is a silicon-based material, and you use a catalyst to create this material, and controlling the timing and percentage of the two components, you can control the porosity of this material, so the percentage of empty in the full in the material, reaching the mechanical and aesthetical property of flesh, of skin. Okay? This is very important because think that with this servo motor, we are pushing or pulling a point, and the behavior of the material is very important. Think about pushing a point of a sponge, or a paper, or a metal bar. I mean, the behavior of the material is very different and very important. But when we have such kind of robot, so complicated, so wonderful, she can do a lot of things with these facial expressions. How can we move this face? And there is another question that comes before. How do I have to attach, for example, these wires to the mask? Where? And the answer is given by this guy here, which is probably the most expert in facial expression in the world, which is Paul Ekman. Paul Ekman, called also the lie detector, is the one who did this incredible job with a Darwinian approach, studying facial expressions from all over around the world. And he has this, he's also the science consultant of Lie to Me. I don't know if you have seen the series with Tim Roth, no? Yeah, so Tim Roth can recognize when a person is lying from micro expressions. And I mean, in that series, Tim Roth is Paul Ekman. So, can you see here? So he collect a sort of atlas of facial expressions, studied them, and he did two main contributions. The first one is this coding system, the FACS, Facial Action Coding System. So he groups facial muscles that are involved in the same action with a single thing that is called action unit. Okay? So for example, an action unit is the one that do this movement. So an eyebrow, okay? The left eyebrow. You need several muscles to perform this movement, but you can summarize with a single action unit. And the second one, the second contribution is this one. He realized that there are 6 facial expressions related to 6 basic emotions that are invariant culturally. So you can go everywhere in the world, and a smile means that you are happy for everyone, in South Africa, in Australia, in the United States, here and everywhere, okay? It's not the same for other expressions. And the cool thing is that mixing, so doing compound facial expressions, you can have other expressions, okay? Like the what the heck expressions, for example, I don't know. And you can also have different intensity, okay? This is called also arousal, we will see this. I mean, why we have this expression? Because they are hardwired, so they are so basic that even several primates have the same facial expressions. You can see the O shape of the surprise, the fact that you show your teeth because you're angry. This is an animal thing. This is something that all we have, okay? So we have to consider this kind of things to do the facial expression of a robot. And this is why the servo motors are attached to the flash-like mask in these points, because these are the action units, okay? This is a very different approach from other kind of robots like Pepper, iCap, because here we have material that we have to move, okay? And so you can see that if you have an orbicularis orbis here, then you have an action unit there, okay? And obviously you can have an anatomical map of expressions, so performing different movement of action units, you can design facial expression for the robots, but it's not a good approach to manually do every expression in the robots. So we prefer another approach, and we refer to the circumplex model of affect. Do you know this kind of thing? This is an emotion representation, an emotion modeling made by James Russell, and we like it very much because we use numbers, and engineers love numbers. So we have this plane, which is made of valence, that is this value. Valence is a quantitative parameter, so for example, you can see here pleasant and unpleasant, and arousal. So arousal is like activation, so less deactivated or activated. And you can put all the facial expression as points in this plane with just two coordinates, VA, valence, arousal. Okay? So this is very useful for several things. The first one, using this ECS, this emotional circumplex space, you have a computational solution. You have again a reduction of information. So instead of going with I don't know, 30 values that are the 30 position of the 30 motors inside the head, you just use one point with two values. Behind that point, there are 32 values, or 30 values, or 20 values, okay? And what? If you start by making the basic expressions, and you put that expression in the plane, then you do something that is called interpolation from scattered data. You take these points, and you obtain values for all the plane, so that I can click here, and I have a facial expression. Wow, this is very important, because I can do dynamics of the face. Of course, if I am happy, like this, and I have to become sad, it's not that I become neutral and then sad. No, I perform some morphing of my face, and now I can do this, okay? And another thing, I can do some micro-expression, some variation of the facial expression. I don't know if you see here, but if I start from surprise and I go in this direction, I can perform a good surprise or a bad surprise. Or I can play with intensity, with arousal. If I'm in the disgust, I can perform an angry disgust or a frightful disgust, going near to fear or near to angry. Okay? This is why we use this. What else? Yeah, dynamics, yeah, I've said everything. So I have to go quick because I have a lot of things. So this is HEFES. I don't know if you have seen it before in the architecture. This is another thing that is very important of using this kind of plane, of representation, which is abstraction. So this hybrid engine for facial expression lets you represent an expression. So that, for example, the plan block can say, do a happy face. But then the actuation block is responsible to translate this point in a facial expression. And the robot can be different. The robot can have different motors. The robot can have no motors at all and have like LEDs inside. In this example, this student, Nicole, used this kind of thing to make a comparison between an avatar and a physical robot. And this is good because both were attached to this thing, no? So different bodies can do the same thing, okay? Can do the same emotions. Well, body. Oh, body is important. So what we did, at a certain point, we want to give face a body, because the robotic part of face was just the head and the facial expression. So we relied on a very good project. This is a French engineer. I don't remember the name, but you can look for this name, Imove. This guy here is fantastic because he created this website where you can download open source 3D components to build your own humanoid at home. But this is cool because nowadays a 3D printer costs like 300 euros. So buying the material, it's not the best robot ever if you have this approach, because it's like a collage of pieces of plastics. But it's very cool. I mean, there is no control, there is nothing, but the body can be printed at your house. So we use this project. Of course, you can also edit the sketch, the CAD files of the components. For example, we modify to house the new Kinect instead of this one. And the hands, we collaborate with a startup, an Italian startup called Loqui. And also this one is very cool. You know what it is? This is a telephone. This is a telephone for deaf-blind people. Why? Because you can use a lip motion, so the little Kinect that you see. You know how the deaf-blind communicates? You can just perform signs with your hands because they can see them. So one is doing like this, and the other one is feeling what the other is doing. But how can you make two persons like this communicate if they are not in the same place? You use this hand, like putting like this on the table, and you do a Skype call, because you do something with your hand, and on the other part, the hand moves, and then you respond, then you reply. This is fantastic, no? So, why we choose these kind of objects? I mean, these kind of things are very, very bad if you want to do some force movement, some grasping. They are not good. But think about this. Signs, communication. This is what we need. This is what we need. Emotions are ubiquitous in the design of a social robot, in the body, in the materials, in the cognitive systems, in everything. So how can we move the body? We can do like the facial expression, so we can move the motors of the shoulder to represent some movements. But why not using our perception system that we have seen before? So doing some trigonometry, you can understand the position of a person and make it reply to the robot, no? And even for the hands. So let's see this video. Okay, this is Aurora, a colleague of mine, which is teaching to face some movements. And this is just a test to understand if the robot is able to understand the posture of his interlocutor, and which works quite good. And you can see the scene analyzer there, no? So this is what the robot is seeing, and is replicating the movement. Let me go forward, and I show you also the part of the hand. She has a fan because her has become hot with motors. So this is something that we have in common. No? Well, we have the brain that is getting hot. Oh, this is a servo board. So you can see all the wires that is going to the servo board. The servo board then is connected to a computer. Oh, this is the lip motion. Look at this. She is teaching some postures and gestures of the hand. You can save them. You can save them. You can have a legend like, say, this one is 1, for example, and this one is 2. And then from the cognitive system, you can say to the robot, perform this gesture with your hand, okay? It doesn't work very well because, I mean, there is a lot of problems in the shape of the hand that they are not the same, but it works, okay? Oh, so last part for the first part of the presentation, which is plan. Of course, tell me when you want a break or if you have questions or can I go? Okay, I keep going. So, plan, the brain, the cognitive part. How should an artificial agent like this, a social agent, reason? Well, this is a bit different from having the robotic arm in the factory because that one is a very structured environment. You exactly know which input you will have, and you just have to be accurate and quick. But these kind of robots have to face the real world, and the real world contains a lot of things that are the hell for algorithms and for computer programs, like plausibility, uncertainty, vagueness, imprecision. How can you relate to this kind of things? This is why they invented artificial intelligence. So artificial intelligence is something that has to face these problems, okay? Okay, so you have a belief, not a certain information, for example. And there are many kinds of artificial intelligence. We have said something about robotics, something about vision. Speech is another thing. You can use artificial neural network. But I will talk a lot about something that I'm sure that you don't know, which is expert systems. And I tell you why. Because the systems are very different from all the others. Are based on knowledge, not on data. Let me explain better with a very explicative thing, that is this thing. So what does, for example, a neural network really understand? A neural network is what you usually use in your phone and in many applications where a program is able to recognize something, like an object. You know, for example, the application that you can take a picture to a plant or a flower, and the application say, well, it's a rose, it's an iris, I don't know. I'm not an expert of flowers, but so, but what is understanding? Let me do this. I don't know if we have the time, but yes, let's play this game. Okay, I will do like this. Quick draw. So quick draw is an experiment by Google AI. Can you see? No. Okay, so I will do the application of the. Okay. So, oh sorry, this is in Italian, but a neural network can recognize handmade sketches. Let's see. Let's draw. A papillon. Oh, wow. In France, perfect. So, a papillon, I don't know. I'm not good at drawing, but something. Okay, it's a papillon. I don't know the English name for it. So we can see if also you recognize what is it. Something like that. I don't know how you can guess, but okay. Pattini. Okay, let me do something that is wrong, like this. So he cannot recognize what I'm drawing because I'm drawing a house. Okay, let the time end. Okay, siren. What will it mean? A siren like the police or a siren like that? I don't know. Let's make something like this. It's a siren, okay. A pickup is the last one, don't worry. I will not play for the entire presentation. I don't know how to do a pickup. It's a pickup, okay. Another one, a glass of wine. A glass of wine, it's easy, it's like that. Okay. Well, good drawings, she said. And he managed to guess 1, 2, 3, 4, 5 drawings, but not the one which is pattini. I don't know, what is the word for pattini? How?
Rollers.
No, skates. In French. Pattern. Pattern. Okay. So the program asked me for drawing pattern, and I draw a house. So let's see why it doesn't recognize this. He said that the network thought, let's say, that your drawing was more similar to one of these one. Okay? While patterns are like that. Okay? So I'm asking to you, according to you, does this program know what are patterns? Or can you ask this program, does patterns have wheels or not? No. It doesn't understand anything. It doesn't understand nothing. It's just, let's say, having a lot of data, which is this. This is the training set, and find some things that already knows that is near to what it's seeing. And if it's not near, if what is looking at is far from every data it has, it will say, I don't know what it is, okay? Or it will say, it's this, but with a very large error, okay? So, this kind of approach is not useless, of course. It's very, very, very important, but it's not let's say, the unique thing that we have to use, okay? Because this kind of approach, this kind of approach is good just for several things, not for everything. Oof. Okay, look this. Machine learning versus expert systems. This is an anticipation of what expert systems are. So, what is, you can read here also data-driven approach, okay? But machine learning is good. Machine learning is the big thing where you can find convolutional neural networks, deep neural networks, everything. So, how does it work? You give to the machine learning the input and the answers. So, drawings of patents. And then, this machine learning algorithm finds some rules to understand what is what, okay? And there are also ethical implications. You know, for example, that artificial intelligence put on Twitter by Microsoft that become a Nazi. Yeah, okay, so it's very difficult because you don't have the control on this. You don't write the rules, you just give data. And then the program finds some way to design rules, okay? That not, almost never are comprehensible. They are not related to something that is explainable in words, okay? For example, for recognizing faces, it's not just a reasoning like, let me check the distance between the eyes and the mouth. No, it's something that you don't really know, okay? While the expert systems, you give the input and you write the rules. Now we see how. So, what we have to use? Well, we have to use both, okay? So, this kind of approach is very good for sensing. So, from taking the real world and recognize some feature, so extract features, classify what the robot is looking at. But then, when you have what is what, then you have to reason on these things. So I see a cat, this is a cat, but let me put some knowledge about cats. Let me also understand what I have to do with this cat, okay? And so you perform some abstract reasoning of the object that you have recognized. You do emotion processing, you do contextual decisions on these objects, okay? So what is an expert system? An expert system is not so recent. Are systems that have been invented by NASA in the '94. I mean, how does it work? It's like HAL, the computer HAL in 2001 Odyssey, Space Odyssey. You are a human user. This is the big computer. You give to the big computer facts, and the computer has a knowledge base. And the knowledge base are the rules. So it exactly knows how to manage this information. For example, you can, this kind of programs are taught to replicate the human reasoning, the human knowledge in form of rules. So, for example, you can have a medical knowledge in some domain. So you give the analysis, the blood analysis to this program, and it tells you with a certain probability if you have a disease and which one, okay, for example. So the knowledge base are the rules. The inference engine is something that, let's say, control the execution of the rules. And the program reply to you with an expertise, with an answer, okay? So the knowledge base, how is represented the knowledge? As I told you, with simple rules. So if this, then that. This is the shape. So this is a super simple rule. If the light is red, then stop. This has to be read like this. If a fact exists that the light is red, this matches the pattern, light is red. I know it looks more complicated than it is, but this is exactly what happens. So the rule is satisfied and it's activated. It's not sure if it will be executed or not and when, because this is a matter of the inference engine. And if it's satisfied, performs an action, that is stop. Okay? This is easy. So a rule is typically made of two sides, the left-hand side and the right-hand side. In the left-hand side, you have conditions or antecedents, and they are linked by a logical AND. So what does it mean? That to be activated, they have to be all true. And these conditions typically are the presence of facts. So I need some information. If I have this information, then this information is true. Or condition about facts, okay? When all the left-hand side is satisfied, the rule is activated, and when it will be executed, it will perform the consequence, the actions, okay, which is the right-hand side. And in this side, you can find actions, creation of new facts. This is very important. So I give you some facts, and instead of doing something, you reason on this information, and you create a higher level information. This is called abstraction. Okay, so you can perform logical reasoning, deduction, induction, or modification of existing facts. And this is cool because you can change your mind. So you have a belief, you ask a question, you receive something that is different from what you think, and so you can change the facts that you know, okay? But the fact that the right-hand side can create another fact, well, this fact can be in the left-hand side of another rule, okay? So what does it mean? That you can chain the rules, okay? And you can do inference. So this is how it works. Imagine that this representation is a rule, so left-hand side, right-hand side. If I have in the environment for example, the presence of these two facts activate this rule, that create a fact that activate this rule. But this rule creates two facts that activate two rules. And so you can design reasoning chains, okay? Even an absence of a fact can activate a rule. And the rule can create new knowledge that doesn't need to activate another rule, but it's just new knowledge, okay? And you can have very complicated reasoning or immediate reasoning. So we can take an expert system and we can integrate in a part of the architecture of the robot for performing this kind of reasoning with what is able to understand from the environment. Okay? How we do this? We substitute the user with the world. Okay? The real world. But why we can do this? Because the facts can be extracted by the world thanks to the perception of the robot and the machine learning approach, the data-driven approach. So I can understand facts autonomously, okay? I can reason on the facts and I can respond not with an expertise, but with actions. Why? Because I have the actuation block. So I can perform some facial expression, some gesture, or if I want also verbal communication, I can also say something. And this will change the world because I will react to this. And my reaction will be taken again to the robot. And so we close the social loop between the humanoid and the human. Okay? Is it clear? This is a bit too technical. I will probably skip this, but just to know that it's very interesting that rules can be written in modules. And this is cool because it's like Matrix, no? You can upload a knowledge to the robot. A module can be related to emotion, so which expression do I have to make? A module can be due to attention, so who I have to look at, okay? And so on. These are examples of rules, I mean, we can go. So at this point, I have a robot that can do expressions, that can decide where to look, who draws his attention, and this loop is closed. No? You can see the scene analyzer here. This is just, I mean, this is interesting. It's a power supply monitor that is understanding if the robot is on for a long time, so we can perform some like he's tired, no? So it begins to move slowly, like you understand that it's, it has been used for a long time. So you can see the information. Here is the metascene. You remember the big file that we have seen before? So the metascene comes to the modules. The modules respond with a VA point, which is an emotion that the robot has to express, an ID of a person that deserves the attention of the robot. Wow, cool. So let's test this. And this is a bit old. This is a younger version of me. And this is the Synthesizer. This is okay, so I'm sorry for this kind of a bit of Parkinson movement because she has a spring in the neck that was too rigid. Anyway, so let's see what happened. Another person enters. She, before look at him, then comes back to me. We are talking, so she is following the dialogue. This is called turn taking. So if you are listening to people talking, this is completely autonomous. You can see the face animator, the scene analyzer. There is a moment. This is the attention. So subject 1, subject 2, or the environment, which is the second. Look at this. I invade the privacy of the robot. So he reacts with annoyed expressions, and look at Roberto, like saying, what is he doing? No? Then we go out. Look at the expressions and the internal emotions that are changing. No? And then comes back to be a bit sleepy and looking at the environment. Okay? So this was a test for this. But we have a problem. What is the problem here? Something lacking. What happens if me and Roberto come the day after in the same lab performing, we are not actors like most of you, but performing exactly the same actions? What the robot will do? The same things. Exactly the same things. So it's not that memory is lacking. It's something better, something that we have. We learn from the emotions that we felt. Okay? So we have a mechanism that links our brain to our body and store this information. And this has been studied by, we stole this from neuroscience, Antonio Damasio. I suggest you this book, is wonderful, regardless what we are talking about. The error of Descartes, of Cartesio. No? And the error of Cartesio is not the cogito ergo sum, is the division between the res cogitans and res extensa, so the material and the spirit. So this is not true according to the brain. He performs a lot of studies to brain damaged patients, and he discovered a particular region of the brain, which is called the ventromedial prefrontal cortex, that perform a peculiar thing. What is this? This part of the brain, which is connected to the somatosensory cortex, to the amygdala, and to emotions, to control of the body, to the feeling of your visceral body and memory. And what happens? That creates a link between what you feel and what you think, let's say, okay? So what happens? That we live in the world, we interact with entities like objects, like thoughts also, and persons, and all these things moves our body. We feel something, okay? And if this feeling, if this bodily feeling, bodily sensation is normal, nothing happens. We are just living. But if it becomes relevant over a certain threshold, this part of the brain creates a somatic marker. Look at this. It's quite easy to understand because soma is body. So it's a marker, a labeler that uses the body. So if the body feels something that is very important, this part of the brain associate this sensation with the inducer of this sensation. And this is the first phase, the labeling. And then you have the recall. When you see again that person that makes you feel bad, or when you have again this thought that brings you to success, well, it happens the opposite. So the path, not from the body to the brain, but from the brain to the body. And what happens? That before being conscious, being aware of this is bad or this is good, your body answers to you. You feel something. So you are thinking about taking a decision and you feel a sensation in your stomach that tells you, no, this is not good for you. Or yes, go. And this is an optimization of the decision making. So it gives you a suggestion. And this is what we emulate in our system. So the first things to do is to split facial expressions, basic emotions that are quick, responsive, and short-lasting, and another parameter that speaks the same language, balance arousal, but is the mood, is the feeling of the robot, is in another time scale, it changes in a more smooth way, in a smoother way, okay? And then we what? Then we put a threshold system. So things happen, I make expressions, so I'm in the elevator, you say hello to me, I respond to you with a smile, but I'm in a bad day probably, so I can perform the same expressions, but I have a mood. But you say, hey, you look nice today. I keep on smiling, but I have a change also in my mood in that case, okay? That it doesn't need to be something that I express necessarily on the outside, okay? It can be an internal change. But this internal change, if it comes in the red zone, then it causes the creation of a semantic marker. And then what? If the robot then look at the subject that goes in the red zone, the behavior of the robot will change, will be biased, okay? This is like creating opinions, beliefs. And we test also this with this experiment that I call the good, the bad, and the ugly. Not because there is an ugly person here, but because we asked to 3 subjects, we designed some rules, behavioral rules in the robot, like, I don't know, having attention to the robot, talking to the robot, or not talking to the robot, saying hello or not, a lot of things, of typical things in a social interaction. And we asked to 3 persons to having a biased behavior. One to be very polite, one to be, normal, and one to be unkind, okay? Then what? Then the subject, the day after, have to come back in the room and to stand in front of the robot at different distances without doing nothing interesting, just staying like this, okay? And here we should see the robot looking at the nearest subject. But what happens? That we put the good guy far, and the robot immediately look with a smile to that person. And you know what? What is strange? That everyone enter this room, this door, sorry. And of course, it's impossible to enter all the 3 guys at the same time. So immediately, when the subjects entering the room, the robot look with an angry face the bad guy, and when sees the good guy, immediately smile. Also, when they are entering the room, this was not provided by us, but this is like creating a behavior, bottom up, like writing the rules, writing the things that the robot, the mental process of the robot, and then the behavior appears. Okay, the behavior is a consequence of the reasoning of the robot. Well, okay, so I have some use cases with theater, and then I show you Abel. What is the time? Okay. Questions?
I have a question of the first part of the presentation. So you mentioned the fact of that the human or humanoid robots can be more protective or more interactive or more powerful than humans. And my question is there any impact, which it can be good or bad, of humanoid robots on ethics, especially when we hear or read on internet that many companies or startups which buy and pay a large amount of money for people to buy their faces after their death. So it's interesting to hear the point of view of someone who make robots. Thank you so much.
Okay. Okay, thank you. So what you're talking about is the ethical implications of this. Yes, of course. And this is why it's very important to me that engineers do not work alone. I mean, because they are thirsty of knowledge and of discover something without thinking always about the consequences. So I can make you a bit trustful on this because there is like a manuscript, let's say, that is signed by the most famous roboticist about the ethics that can, the limits in the ethical implications and what you can do or cannot do. So yes, it is very important, and you don't have to do things beyond human power, for example, but in some case you don't need also to have any limits or constraints. For example, let's think about the application with people with Alzheimer. We have non-communicative patients, okay? So we need to go beyond the capabilities of a doctor without instruments. And we have to provide the doctor with this kind of instruments that perform some capabilities that are not reachable for a human. So, I mean, it's a very tricky thing. It's very important to just one thing that is said by Asimov also. So the robot does not have to harm someone, okay? But also this is tricky because if you have a car, for example, moral decisions. I mean, this is we need an entire lesson on this. But yes, this is super important. You have always to have an eye on this to say, okay, what I'm doing, but what are the consequences of what I'm doing? So yes, ethical implications are always important. Okay, let's go on. I'll show you this thing. This is the funny part. So in this case, we have a kid from 20th Century Fox coming in our lab because they have a trailer of Morgan, which is a movie produced by Ridley Scott, which director is Luke Scott, which is the Ridley song. And for a promotional reason, they have this trailer made by an artificial intelligence. So Watson, which is an artificial intelligence by the IBM, create a trailer selecting the most emotional parts of the movie and creating this trailer. And their idea to promote the movie is to do this teaser in which robots react to the trailer. So this is a teaser in which expressive robots react to the teaser. In this case, we have, this video has like 1 million views. I've seen this yesterday when I put in the presentation. And here you can see face, you can see another robot. This is the trailer. So things are happening in the trailer, and they want to use the expressiveness of the robot. But what? How does it work actually? Like many things that when you see robots on TV. So this is a script. This is not in an autonomous modality, okay? Because they want to be sure that the robot does the right expression at the right moment, of course. So in this case, we have a script execution with also predetermined timing. So the robot has to perform this exactly micro expression for tot seconds, but then the scene change becomes scary, so the robot has to do a scary face, and so on. So this is the first example of the usage of the robot in this context. Okay? Another use case. Here we have been invited by a big association of lawyers. And here the lawyers were scary because they were thinking about, it was a convention about the thing that, I don't know if you know Italian, but here is written, quando I robot apriranno lo studio. It means when the robot will open their study, no? as lawyers. So they were questioning about what will happen when this kind of robots can do this kind of jobs, okay? In this event, we have a presentation, like the one that I'm doing now, and then they ask also for a representation of a possible future in which the robot receives a client. In this case, I also play as an actor, so I program the robot, and we have in this theater this representation, this theater representation of the situation. And in this case, I have colleagues of mine behind the curtain that, again, we have a script, but we have predetermined actions. And to be sure that everything works well, the timing was not predetermined. So there is a person that launch the sequence. Okay, so this is the time to do this. This is the time to do that. Okay, and this is another use case. This one also is cool, and here again is different. This one was the first, they say, I don't know, you probably confirm or not, the first robot opera. So in an opera, a lyric opera, in which a humanoid robot has sang, and also, so the robot sings, the robot moves, and interact with the actors. How do we do this? We do this with a lot of meeting in our lab with her, which is the real human version behind the robot, and she's a lyrics singer. And we study the movements that she made and the things that she has to do during the performance. And we replicate the movements on the robot, but we didn't program them. In this case, me and another one were together with the musicians. I don't know if there is an image. No, we cannot see here. This is the end. No, it's not visible. But we were behind the curtain together with the musicians, and we were playing with the robots. Meaning that it's like doing music. I'm also a musician, so I love to do this kind of things. So I have behind the curtain the singer next to me singing. I was looking at her, and I was moving the face and the head of the robot as the actress. Another one was controlling the arms and the body, okay? And so the robot in this case is teleoperated. This is a modality that is used also in many experiments, which is called Wizard of Oz. So even in scientific experiments, in papers, you can see that some robots are controlled by a teleoperator, because probably you are interested in the human reaction and not in testing something on the robot, no? And this is another case. And then there is another case, and this is the maximum of the capabilities of the robots, in which FACE has been involved in this tour, theater tour, by Beppe Grillo, which is a comedian actor. I mean, he's also a politician, but this is very difficult to explain. Italy is a strange country. Anyway, I don't want to talk about politics. Anyway, he has this show in which involves a lot of technology. So he has prosthesis that we made in our lab, and he has FACE on the stage. In this occasion, FACE was completely autonomous. So we agreed together with the director of the show the rules, the behavioral rules of the robot, and the actor interact with the robot. So this is improvisation. And this is very cool, but we have pros and cons. Why? Because the actor should exactly know the rules inside the robot, or must be very able to react to the robot. And this has not been made as we want, meaning that the actor was very focused on the show and not always remember, for example, that the robot doesn't react to what he says. So this is something that has to be taken into account. But I tell you also a good thing. There has been a scene during the show in which the actor goes very close to the robot. He was talking about corruption, and so you see, ma ti rendi conto? Which is like, can you believe it? No? And the robot was looking like smiling. No? And because the robot was smiling to the actor say, "Why are you smiling?" shouting. And the robot has a rule for this, that if it's disturbed because one is talking too loudly, the robot removes the attention from the subject and looks at the point with the measured light. Okay? And in that occasion, there was a spotlight in the middle of the public, of the people looking at the scene. So the robot reacts like this, with the scary expressions, looking at the people. And the entire theater starts laughing aloud for this kind of scene. And this is improvisation made by a robot. This has been an incredible occasion to experiment this, no? So, the more you give autonomy to a robot, the more precautions you need to have. Also the actors, or you have to test it a lot. Otherwise, you are very sure of what it happens, but you don't have any surprise. Let's say during the show, it's not an improvisation. Okay? Anyway, it's the same also for acting, I suppose. You can have a very precise script, or you can have an improvisation performance. This is something that we can do also with robots. Okay, let's go to Abel. So, Gustav, a genius, the animatronic genius. So why we contact this person, and who is? Gustav is, as he said, he's an artisan. So he's a handcraftsman. So he's someone that creates materials, that create creatures, sorry for the play of words. He has the ability to combine design, anatomy, translated through mechanics, and he studied the movement and the aesthetics of engineering's creator. So he's able to create these things that are used where? In the movies. Okay? So why we contact this kind of person? He's not an engineer. But if you want to create something that is able to convey emotions, to be very expressive and emotional to others, please don't ask this to an engineer. I mean, I can say this because I'm an engineer. Engineering are boring. I mean, they don't know exactly how to impress someone by an emotional point of view, okay? No, jokes apart. This kind of people knows since years and decades how to create something that is expressive, that conveys something, okay? I remember when I met him for the first time in his study, and I find this very scary creature. He was working for a Swedish horror movie, and he created this creature which was a middle between a crow, so a bird with these black leaves, and but has hands of a child. It was very scary. I mean, it was already scary. You don't need to move it. It was very impressive. And he is a genius in this kind of thing. And the approach that he has is very important. He starts from a concept. He starts from the material. And then he understands how to move this and how to create an emotion. It's not mechanics. It's not that you start from gears and wheels and then you see what happens. It must be a reverse proceedings. I mean, it's something that jump up and down. So you do something, you test. He will also show me that he tests the mask with his hands to understand how to move it and where to attach the mechanisms. And he has an incredible inspiration from the human anatomy, okay? So we start from the concept, and I send him a mood board of images. So what is the concept here? We want a creator that is like an angel, something like you don't understand. You know this one. This is Eleven from Stranger Things, no? I mean, you know that she has superpowers. You don't need to see them. You feel that is like that, okay? Or this is another project from a Dutch photographer who takes picture of kids before and after the sexual development, so pre-adolescence and then adolescence. And we want to create, I mean, you know David Bowie, Tilda Swinton. We need this kind of androgynous, interesting aesthetics that makes you curious of knowing these agents. And it has no gender, no indications. It's like no binaries for the communication. When you go, I don't know, at the bank, you see a person that has some clothes, and you know that it's functional. The communication is functional. You know what to ask. You expect what they will reply. You don't go to a bank and ask, hey, how are you? No, you don't do something like that. So we need a mysterious, with a perceived intelligence and a strange creator, but also gentle in its aesthetics. Okay? And another concept is that he asked me, how can we do with the parts that are difficult? Which are the parts that are difficult? The joints. Because when you do these kind of things, the skin can do some strange things, no? And if you have to adjust the motor, or if you have to intervene in some way to the mechanics, you need some access points. So, how can we do this? And I discovered that Gustav is a great fan of Ghost in the Shell, which is an anime and also a movie. And so he proposed to use this kind of split lines, no? And to leave some part exposed for another reason, which is scientific. In certain use case, you need to show to people that it's a robot. In other case, you have to hide it. So we have, for example, a whip for the head. We have clothes. Otherwise, we can use it freely, so you can see that it's a robot. So they start, look at how artistic is this process. She is called Livia Turco. She grew inside the Madame Tussauds museum. So she is very able to create copies of humans. No? This technique is called life casting. They use this Asian colleague because has very tiny hands, like the one of a kid, and they start from the hands and they produce this master. So, and look at this. This is a creation of a statue. So this is an artistic work. It's not something that an engineer can do. I have a video for this, so just to show you some picture. So this is the part of Livia. And here you can see the split thing, no? So the body before is entire, and then is like this. So you have motors, split lines where you can put skin, and you can remove that. Okay? So she create the master, and then create this part is the one that you launch in the trash at the end because you don't need it. Because what you really need is not this, but it's these parts, which are the molds. Is where you put the silicone to create the skin. Okay? So they create the molds, and then they create the flesh-like materials put in the skins. You can see here the master that is almost broken, no? And he creates everything. The skin for the hands, for the face. And then what? And then the best part for Gustav, mechatronics, he is his main part. So mechanics and electronics merge together to create movements, starting from the materials, starting from the creator, from the concept. Okay? You can see the anatomy. Can you see here? And there are a lot of mechanisms that he is able to do to create very reliable things. Like, look at these things of the eyes. We have these yellow circles that where you put then the eyes, and then you have these half circles that are conceived to follow the eyes, because you have this squiddy thing in robots that when they look up or down, you can see a hole inside the eyes and look through. So he performed these kind of things of the orbit following the eyes. I mean, these are details that are super important to fall not in the uncanny valley, okay? And probably we're not reached the point, but we are making steps. The hands are amazing also. So let me show you this video. This is Gustav. This is the very beginning. He starts from a frame. Okay, this is the frame of the robot. There is nothing here. And then what? This is long, so I will. These are videos that periodically, I mean, we have a trend of email between me and Gustav, like 100 emails, and I always ask for some videos reporting the evolution of the work, and we discuss what to do, no? So look at this. How manual, how artistic is this part of the process. This is Livia that is creating the master. And it's exactly like doing an artistic sculpture. Okay? Can I ever do something like that? No, absolutely not. So it's taking shape. I mean, this is very reflective for me, because think about that, to make a robot, you always need a human if you want to do a robot like this. I mean, if you want to do like at least the first, then you can copy probably the robot. But you cannot automatize this process. Okay. Look at the distance for the anthropometry. Oh, sorry. I see. I want to go forward in the video. So here are the molds. This part is a bit scary, but it's just the negative of. No, this is trash. This is nothing. Yeah. And this part is about Gustav. I hate this video because there is a point in which he's drilling a piece and looking at the camera and saying, "What are you doing? If you hurt yourself, we are." I mean, it cost me a lot to convince him to do these kind of things, because he's really, not shy, but he don't like to take pictures of himself or movies like this. So he doesn't know if looking at the camera will work. But anyway, great. This is just the inner part, and then there are other parts. Oh, another difference. Here we have very different materials, long-lasting materials. This is not 3D printed skull. This is handmade by Gustav with machines, with CNC, with things that he has in his lab. And I want to show you also a bit farther. Oh, these are the eyes. Look at the jaw, no? The mechanism of the jaw. This is the part that I was talking about before. And I'm quite sure that we can reach very believable movements for the speaking also, and for the gaze with such kind of mechanisms. Well, so this is the result, is Abel. Okay? And yes, we have said, he has 43 servo motors, and servo motors are different because there are motors inside the head, but there are different motors, more expensive, more efficient for moving weights, so arms, hands, the neck, okay? Of course, we will use the social emotional artificial intelligence that we have seen before also for Abel, and we will develop the software. So, okay, a few things of Abel. Abel is under development continuously, so we have a lot of students that are working on. This is from the thesis of a student of mine, which calls Gabriele Cesina. And we have, as I told you, some very different actuators. There are still servo motors, but they are dynamic. So they are very silent. It's incredible. We don't have the audio, but I mean, moving the body of face that you have seen before is like a lot of noise. This is very soft, very silent, and you cannot see any effort in the movement, okay, when the robot moves. And they are very cool because you can control them in speed, in current, in torque. You can, for example, decide which kind of profile of acceleration to perform. Why? Because, of course, if I wanted to do a robot that moves, if the robot moves like that, this is not human-like. We don't move like, with a linear acceleration and velocity. We used to move slowly at the beginning, quickly in the middle, and slowly at the end. So we need to design some curves, in some profiles, like this, in velocity, in acceleration. And this is what we have done. And for the neck was so complicated because it was similar to a human neck that we need to do reverse engineering. So what we have done, we have moved with the hands, the head of the robot, and see what happens in the motors to understand how to move the head, okay? Also why? Because he's an artist, so he does not have CAD files or computer projects. We have to study the structure with the reverse approach. But look how, this is a GIF, so it's a bit, anyway, look how realistic and fluid is the movement, no? For the neck. And something similar has been made also to replicate the motions. And he's Gabriele, he designed a software that works like this. You can put let's say the resistance of the robot to 0, so but standing. So you can, for example, put the arm here and the arm stands there. So he's compliant, but after, I don't know, a time that you can decide, like 15 seconds, so you put manually in a position, and then it becomes rigid after 12 seconds, and learn that position, store that position. This is easier because it's like taking a person and they put your body like this. Well, it's very easy, no? And you can study also this profile of acceleration that I told you before, just performing, accompanying the movement of the robot with your arms, for example, okay? Then we test also different parameters, let's say, no? So profile velocity. So this is bad. It's a bit, no? It's a bit robotic. But if you change these parameters, you can perform something better, no? This is a bit smoother. It's more calm. It's more similar to a movement that we can do, okay? This is just random postures there, no particular significance. But there is also a visible change, no, according to the parameters that you use. Then what? Then we have some compliance, and this is because for safety, let's say, no? You need the robot, if the robot has to reach a point and find an obstacle, it doesn't have to put all its strength to reach that point, because you can harm someone. So, as we said before, also for ethical reasons, so you have to pay attention to this kind of things. So, we can make that the robot resist to some perturbations, let's say, but we can decide a maximum absorption of current that corresponds to an effort, a physical effort, that can make. So you can decide how compliant the movement is. No? So, then what? Expressions. This is a whip I don't like too much, but this is a service from a national TV of Italy. And these are some expressions. We start from doing it manually. We can do better expressions than these. And we will do this kind of thing using another approach that I show you. This is very difficult to explain. I mean, what is a multimodal deep Q network is not something that we can do today. But this approach, which is in the branch of reinforcement learning, works like this. The robot can learn by the observation of humans. So how does it work? In reinforcement learning, you have rewards. So you have a reward according to how near you are going to an objective. Okay? So if you are very near to what I'm showing to you, I give you a reward. Otherwise, I give you a penalty. Okay? So in this approach, you start with random things, in the expression, and try to understand which are good and which are bad. And you learn and you improve. Okay? And we can start to do this with a data set. This is probably the one that we will use. This is a work that we are doing with another student. This is the YAMOCAP database. And look at this. Here we have approximately 12 hours of audiovisual data with motion capture of face. There are persons that are annotating, like this. Here there is a facial expression that is of upset, and so on. So all this information are given to the robot. And you know why we are doing this? To go beyond a problem that we have with this kind of robots. Then when the robots speak, cannot make an expression. So to speak, he has to stay neutral. And it's a very strange thing, if you think, no? Because neutral and then smile. Neutral and then smile. It's not good. Because you need to, and it's very difficult, no? Because you have to merge the facial expression with the movement of the mouth. How can we do this? Not manually. But with this approach, it can work. Because we have videos of people talking with different emotional states, and the robot can try to reach that level. So I will tell you how this goes. And this will be made in collaboration with a startup that is called Emotiva, which is similar to the software that we have seen before, but it gives us the information about the single action units. And this is important because otherwise we cannot do this kind of training, okay? Just knowing if one is happy or sad. We have to follow and to make the robot follow the muscles, okay? And this is the last thing about Abel that I want to show you. I think that is also interesting for you. That is personality. So, why don't put a personality on the robot? But how? We cannot use this kind of approach. This is the MBTI, so the Myers-Briggs Type Indicator. There are a lot of this kind of tests, the Big Five, the Hexaco, you probably know some of them. How do they work? With a top-down approach. You make questions to people, and you understand some dichotomies, like these 4 dichotomies. If you go here or there, you end up to go in one of the 16 square, that are also the 16 types of personality of Jung. Anyway, this is out of the topic. So, this is not a good approach, but we have found another theory by Michel and Shoda, which is very cool because it is a bottom-up approach. What does it mean? It doesn't try to understand the personality from the outside, asking questions, but it's trying to determine how this personality comes out from that person. So they want to open the black box, the mind of the subject, and they want to explain and to understand the cognitive affective processing system that create this personality. This fits very well with our system and with our scope because we want to generate a personality. We don't want to ask the robot which personality he has, okay? And this fits very well also with the problem that we have seen before because this can be facts and rules, so that you can link together. And they are the cows, the cognitive affective units, encodings, beliefs, expectations. They also explain why a certain type of personality does not behave always the same, because you have contextual variation. You can have an emotional state of the subject, and this implies variation in personality. Then, of course, you have recurrent behavioral signatures, as you see here, no? So if situation, then behavior. But in the middle of the situation and behavior, there is a person. What happens in this person? This is the question that we are trying to solve. And we did this creating two examples of personalities with another student in his thesis that works on personality, and create this network of beliefs, expectations, competencies, to create then a behavior. This has been done initially just to test if the system works, and it works. Now, in experiments that will be conducted in the next year, we are designing this in collaboration with psychologists of the EMT in Lucca, and we are trying to ask people not which are their personality, but how do they think that the internal process of people that having some personalities. For example, I say, how is your brother? Okay, okay, you tell me how he behaves. Can you tell me why he behaves like this? What are the beliefs and how are they connected? So we are trying to extract this kind of schemas from the people and then replicate it in the robot. And then we evaluate it. How? Calling other people, making them interact with the robot, and then asking to do a personality test of the robot to these people. So can you, the first question is, does the robot, according to you, have some kind of personality that you recognize as a human personality? Yes, cool. This first point has been done. So, this personality, do you see or believe that has some mental processes and which they are? And if they are exactly the one that we ask to the persons and we implement in the robot, and the people manage to understand this kind of internal reasonings, well, we are doing real personality in robots, okay? Imagine that you can have an actor, you can make it autonomous, and you can design also the personality of it. What does it mean? That, for example, if I'm explaining something and I see someone smiling, I can be, according to my personality, I can be happy for this because I'm explaining good, what I have in my mind. Or I have another personality that, hey, this person is laughing at me. And I block myself, I become rigid, I stop talking. So you can design this kind of personality inside the robot, thanks to all the things that we have seen until now. So this is a summary of our objectives with Abel that we want to. I think that we discuss almost everything. Yes, the integration of the affective computing, the new algorithms that we will study a lot of verbal communication, because Abel can do this. Abel can also perform some movements that can be believable. So we will study this together with computational linguistics from the CNN. We have a collaboration with experimental economists to study trust. So when you trust a robot, there is one way that is very effective to understand this. Putting money in the middle. So if you have money and you are playing a gambling game with a robot, and then you change a few things in the robot, like you keep it emotional, you keep it more cold, or you change what he said or not, and you see if someone trusts or not the robots. And this is very interesting for the economists to understand the behavior of peoples, because many things are known and many experiments have already been done between persons, between humans. But what happens with this kind of agents that will be between us in the next years? This is something that we don't know and we have to study. Then what? Yeah, verbal communication. The body gestures that you have seen before, so we have to study how to make them the most reliable and expressive as we can. And the generation and adaptation of personality and behavior. This is something that we are going to use also in applications, in medical applications, because a therapy, an interactive therapy, can be more reliable with a certain personality. The doctor itself changes personality according to the patient. more imperative, more effective, depending on the success. So the robot also has to adapt, okay? And, okay, I think it's all. So I leave you with these wonderful pictures of Massimo Berruti, which is a photographer, a very important photographer that is following us from the beginning of this story. And that's it, I think. Yes. So, thank you. Yes? I will give you the microphone.
So can we see if you have some question in audience, or even if you have some question in Zoom, you can write, perhaps it's better. And here, do you have some question, perhaps? So,
Thank you very much. I have a quick question just to start the discussion. It was more about context and emotions as we are working in theaters with things, let's say something happens on stage and there's a reaction. Like, I don't know, a bird is falling dead from the sky and there's a reaction, this kind of context. Because when I saw how Abel was set up in the stage to be apprehended by the participants, I always wondered what other things can he perceive of the environment? How can we analyze, she actually analyze the environment and, let's say, connect these two parts together of context, of social, non-human maybe context with his emotions, with the emotions he perceives. Thank you.
So I will come back to one of the very first slides that I show you, which is this one. And the answer to what you are saying is probably this part, the modularity of the system. What I mean, this is not a closed system, okay? And for example, in the meta scene, I can add information coming from any kind of software, because this kind of abstraction of information lets you disconnect the part of the system in a sense. They are connected because they communicate, but if something changes somewhere, I don't care if I am elsewhere. So what does it mean? That I can change here, and I can put a bird analyzer. So a software, if there is someone in the world, because I really don't know, but design a software to detect falling birds, well, you're welcome. You put that in my sense block, and I will put this information in the meta scene. So in the meta scene, I will have falling bird, yes. Or falling bird, I don't know, a seagull. So even the type, if it's trained to understand which kind of bird. And then what? I come back to this one. And then I can have, in the situation, the possibility to recognize not the noisy environment, but a birdy environment full of birds that are falling. And I can design a lot of things. For example, the encoding is like the internalization of the fact. So the feature is in the situation, and then the feature is inside me. So it's like primary recognition. I know that there is a bird, fall, and it's a seagull. Okay? But the encoding can activate a belief. A belief can be someone shot to a bird. This belief can activate an expectation. Everyone will fly away from this situation. It can activate a competency, perform a scary expression, and another behavior, like say, why this bird has fault. So, you can do almost everything that is reachable at the state of the art and include in the system. This is why modularity is very important, because it's not closed. And another thing is that it's not monolithic, meaning that it's not like the hierarchical architecture that I showed before. What is the main problem of this kind of architecture? Let me show this slide. Here it is. No. Okay. So what is the problem, the main problem, the technical also problem here in this case? That is monolithical. So what happens? An engineer immediately tells you the problem of this chain. If a program, if something crashes, all the system crashes. Okay? We don't have this kind of thing in our system because it's hybrid and because we have rules and the robot will always do something. And it's the same like us. If I cover my eyes, I can always hear. If I don't know how to solve a mathematical problem, I will probably be able to sketch drawings. So it's not sequential. So you can add properties, you can add capabilities, and you will always have some reaction to the robot. Of course, if you don't have the eyes to see the robot fall, the bird falling, you will have no reaction, but it's the same for us. If I don't have eyes and I don't have ears, I don't know, I can smell the odor of a bird, probably. If I have something that, I mean, it's exactly, like, not exactly, but it's exactly as in our case. We also have a meta sim. We don't know which is the sim. I mean, this is a bit philosophical, but the reality that we know is the reality delivered by our senses, okay? So, if you add a sense to the robot, you add a perception of reality, and you can use this knowledge as secondary cognition at that point, because you know that there is an object, and you know what to do with that object. And this is another thing, and I go to another slide, which is a property of the expert systems, which is this one. If you have, let me check, I can take this. Actually, the system is this one. The facts are not in the system. This is something that is very strange for a computer program. You don't have to declare variables, you don't have to have the data inside the program. You just have the knowledge about how to treat that data, but you do not expect the kind of data, the order of the data. So you don't know the input, but you have the ability to manage, to process this input. Okay? So if you have a sensor that is able to understand a fact, and you have a knowledge that is able to process this fact and knows what to do with this information, then you will have a reaction, an action. Is it clear? Okay.
Just maybe some more question about the future use that you are thinking about for this kind of Android robots, and in particular if you can tell us something more detailed about maybe the strong points and the pitfalls actually also of using these robots in let's say a scientific society which humans and robots will live together. Actually, I think it's the last part of your last slide.
Yes, yes. I mean, it's not easy to imagine what will happen in the future because things are changing in a higher and higher velocity. It's not the same velocity. So yeah, I can't prevent and improvise what will happen. But I think that we still, regardless of all the things I've said, I think that we have still to face this problem. This is a problem that we have. I mean, I'm sure that you also feel a bit of eeriness in your backbone when you see some image of this kind of robots, and it's normal. I mean, but there are contexts in which they probably can be used, and these contexts are where humans are not well accepted, and robots are. What is an example? I mean, this is strange to say, no? Let's take the autistic children, okay? What they have a problem. They have a difficulty in the association of facial expressions and emotions. So what happens? This is something quite recent, in the last 10 years, that has been discovered. So what is the problem? That if you don't follow them, they will build their own dictionary. So they will build a dictionary in which a smile is a symbol of aggressiveness, okay? And this is a bias that they will have for all their life in inputs and in outputs. So if they see someone smiling at them, they close themselves and say, why he is angry with me, for example. And if they want to show you, if they want to tell you that they are happy, they will probably throw everything down the table, and you can't understand what they want to tell you, okay? So how can you help them? With actors? Yes, of course. So you can have a psychologist, and you can have a human actor that react to tasks. So you can play games, you can do things, and then there is an actor that performs the correct, let's say, it's not correct, it's the common language. So the common language expression for that situation, and the child learn. But the child don't like to look at in the eyes of persons. This child don't like to interact with real people. This is why we use robots, because they are definitely not less intelligent than us. They are different probably, but they have different language, but they completely understand that it's not a human. And they are happy with it. This is measured. They have more eye contact. They have less reaction that we have measured with the wearable sensors that I've shown you before. So they don't have this scaring reaction. And the therapy is calm. And the therapy is more effective because they look in the eyes, the robot. And the robot, with the extremely capability of repetition and precision, always teach this expression, which is the most common for the people in that situation. And in that way, you are giving to a person the possibility to have a social life for all his life, thanks to a dictionary that has been taught by a non-human agent. So this is an example. The other example that I told you before is the one with non-communicative patients. So you can do whatever you want, but you never know what is working or not, because you can't feel the reaction in this kind of patients. But if you use this tool as a tool, I mean, it's not. I don't care of these things about humanoids substituting us. This is not happening. I mean, so these are tools. These are research tools, and are tools that a doctor or a physician can use. So for example, a psychologist. I mean, if you are a cardiologist, you have instruments, okay? But if you have a psychologist, you don't have instruments. I mean, not such instruments to include a person in a social interaction that you design together with engineers, and then see the reaction. Let's think about, for example, the classification of a mental disease. No? What do? You ask the people to compile questionnaires, but you don't know how they are feeling when they are compiling the questionnaires. What about if the questionnaires is made by a robot that is able to understand also what is the reaction inside the body of the subject? And then what? You can also design the paths of the questionnaire, because the robot initially just say, hello, my name is Abel, what's your name, and some, useless stuff. But then, what about your mother? And you can see that the subject is talk about the mother, but inside has an emotional, physical reaction that is very important, and the physician, the doctor that is with you, tells you, can you design me this questionnaire that if the reaction is this one, the questionnaire goes deeper in this argument, or can you design me a questionnaire that avoid this argument if the reaction is that? So this is an incredible instrument that can be used for this kind of persons.
From a theatrical point of view, your presentation was very interesting because I have the impression that your approach with that prototype moved in a meaning that from phase you has what we can call in theater studies an approach like a puppet. You teach to face how move, and you show us a video where a person teach the movement to the face, to how face have to learn that movement. And in Abel, of course, you show us how you build the body, but in fact what I feel that you try to go in a direction where Abel can be a sort of not puppet object, like autonomous, or if I could understand, there is a big part of autonomy. And my question is about audience. I mean, in which moment or not, but you put the audience in your process of improvement of that prototype in terms of complicity, in terms of empathy, how the audience help your work, or in which moment the audience enter in your work. If I'm thinking at your experience in the opera stage, how felt the actor and how the feeling of actor improved to face, and if you have plain some experience in the future with Abel in the theater stage.
Okay, I will answer this and to Salvatore also, because it's another future possibility. So I think, I'm quite sure that an interaction between humanoids and humans brings advantages for both. What I mean? I mean that, first of all, this kind of objects that are creators, let's say agents, I don't know how to define them, but they are like mirrors for us. Okay? So these are used, of course, as a research tool. Why? Because think about personality or behavior. I am a psychologist or a psychiatrist. I have a model in my mind of behavior, and I say people behave like this because they think that. I can test it. So I can put it in the robot, and I can try to make him interact with a person, and I see if things evolves like I have expected. And this is one example. But another example is that every time you model something that regards a human, you are better understanding. And this is in the principle of modeling. When you model something, you have to reduce something. So because you cannot make a copy, a replica that is exactly the same. So you take the most important parts. But these are the most important parts for you. Then you put it in the robot, and you see that something is missing. So you take the discards and say, okay, so probably this works for, is helpful for a function. And you put this thing together in the model, and you see the model that improves. And so you better understand the human thoughts, the human behavior, and so on. Then there is another example, and I think this is probably a future thing. And to explain that, I take this slide because I forgot to say something, and this is exactly what you're talking about. This part, which is a reinforcement learning algorithm, is learning by what? By a data set. But there is an evolution of this approach, which is called interactive reinforcement learning. So, what is it? With the first part of the work, the robot reached a good capability, okay? Just looking at the data set. But then, the robots will interact with people. Interacting with people, it will improve more. It will adjust, because what he has learned is not so near to the subject. And so it will be amazing to see, for example, if I perform some movements to express some emotion, and then I put the robot in front of a subject, and first of all, does he understand? Does he smile? Is there a positive reaction in the person? Yes, so this movement is good. And then the robot can say, can you show me the same movement? And the data, this data about the new movements that he is looking at, becomes new data of the training set. So the learning of the robot never stops. And he keeps on learning while interacting with people. So he will learn probably the best way to communicate and the best way to replicate, to express himself like us, probably. This is what I hope.
Thank you so much. I think that our time is done. Thank you very much for your inspiring presentation. I hope that in the future can be perhaps make some collaboration between theater and Abel and that wonderful prototype. So this is our last webinar for the first semester. So perhaps, not perhaps, certainly we will organize other webinar in the next few months. Thank you very much, and we will see you soon.